All right, so let's review associations where we spent the first few weeks of the course. So we know that we use the word association as a general term to describe whenever two variables or two quantities are related. And specifically, we say that two quantities are associated when, for whatever reason, knowing the value of one quantity tells you something about, or in other words, narrows down, the possible values of the other. And so a lot of business analytics is preoccupied with association analysis because they want to leverage information that they do have to learn something or to exploit that to learn something about they don't know. So how can they use information about how much money was spent on advertising to predict or figure out how many sales are going to result? So one important thing about association analysis was casting the two quantities into the roles of X and Y. And we had seen that actually the statistical analysis, whether or not statistically the two variables have an association, doesn't really matter depending on what's Y, what's X, but graphically this was a key distinction. And so the way to remember which is X and which is Y, well, Y is always the quantity of interest. It's the thing you're really studying. It's the thing you wish to predict. And X is the quantity that you're using to make those predictions. All right, I have a slide that reviews a few examples. I'll skip that. And related to the word association, which is just a general word to describe when two variables have a relationship, we also have the specific word correlation. Now, correlation refers to a very particular type of association. Two variables have a correlation when the average value of one increases or decreases linearly with the other. So for two variables to be correlated, they both have to be quantitative, inherently numerical, and if we look at a scatter plot, the relationship between them needs to be linear. So be aware of the difference between association and correlation. Correlation is just a specific type of an association that describes a linear relationship between two quantitative variables. All right, so let's talk about associations between two categoricals first. What do we need to know about this? Well, the first thing you need to know about is how to visualize the association. So we've used Mosaic plots to visualize a potential association between two categorical variables. And what the Mosaic plot does is it gives a segmented bar chart for each level of X. Now remember, the segmented bar chart splits down the possible levels of Y, and the area of the segmented bar is just proportional to the frequency of each of those levels. So here we're studying the association between the class level, freshman, junior, senior, sophomore, and gender. So freshmen are the very super dark bar, juniors are the dark gray bars, seniors are the bar right above that, and then sophomores are the top bar here. So we can see that for females it looks like freshmen are very, very rare, seniors not quite as rare, and then slightly more sophomores than juniors. For guys, over here we see that there's a pretty large fraction of guys that are juniors, followed by sophomores, and like with girls, freshmen and seniors are both relatively rare. So the segmented bar chart just plots the mosaic plot plots the segmented bar charts for each level of X here. On the far right is the marginal distribution of Y, just the overall frequency distribution of each level here. And what we're looking for to determine if there's an association is, do the heights of the shaded regions match up from left to right? If we see a big discrepancy like what we do here, we suspect an association because knowing X, knowing if you're a guy or a girl, really does narrow down the possible values for Y here, class level. In essence, if you're a guy, well, you're much more likely to be a junior than if you were a girl, where in fact you're more likely to be a sophomore than a junior here. So to visually gauge for the presence of an association, look for the discrepancies between the segmented bar charts. If you see noticeable discrepancies, you would suspect an association to exist. So here's a slide that outlines what you need to know about mosaic plots. I'm going to skip this slide and move on and talk about the statistical test. And here's the fact of the matter is that even when there's no association, even when all the levels of x have the exact same distribution of y, you're still going to see slight discrepancies in the segmented bar charts. And so that's why we need to run a statistical test to see if those differences are statistically significant. So remember, what we say is that an association is statistically significant if it is unlikely, meaning that there's less than a 5% chance, that the Mosaic plot would exhibit at least as large a difference in the segmented bar charts as what you actually see in your data here. So a statistically significant association is one where the differences in the distribution of y between the levels of x is large enough that that wouldn't just happen by chance. A better explanation is that there really is an association going on. And one thing to remember is that when we do talk about statistical significance, the idea of practical significance, whether or not the association is strong or important, is a whole different thing. So a statistically significant relationship may not be strong or hold any practical significance, especially if that sample size is large. When the sample size is large and we calculate p-values and significance, it might be the case that a very, very weak association turns out to be statistically significant, unlikely to be produced by chance. So keep that in mind. And then also, if you do find that the relationship is not statistically significant, well, the lack of significance does not mean that there's no association, just that if there is one, it was too weak for you to detect from the data. So usually when you find a lack of statistical significance, that's always going to imply a lack of practical significance, because if there did exist an association, it's too weak really for you to care about. All right, so how do we actually perform the statistical test? We suspect an association when we see discrepancies between the segmented bar charts for each level of x. So what do we actually measure from the data to quantify whether or not that discrepancy is statistically significant? Well, in fact, we don't look at the segmented bar charts. We look at something a little bit more numerical. We look at the contingency table. So if you remember, the contingency table breaks down each level of x and each level of y and tells you how many individuals had each combination of levels. So there were 131 guys who were juniors in the class, 45 females who were seniors. So be able to talk about the contingency table. Tell me what these numbers mean. Down in the margins, we have the marginal distribution of y here. How many total people were freshmen, junior, senior, sophomore. And here on the right margin, we have the marginal distribution of x. How many girls and how many guys. And here's the sample size, 579 total people in the survey. So when we do the statistical test, what we're actually comparing are the numbers that we see in the contingency table to the numbers that we would have expected to have seen had there been no association between x and y. So that begs the question, okay, well, if there was no association going on, what numbers should I expect here? Here's my table of expected counts, but how do I actually get them? Well, as an aside, we have formulas actually that tell us how we get the expected count, and it's actually really easy. We basically look, if I want to know the expected count for this cell right here, we look at the row total, multiply that by the column total, and then divide by the grand total. So 250 times 78 over 579 is 33.7. Notice that's very close to what I actually observed, but as I scan through all the entries in the contingency table, I see a bit of a mismatch in some places. 108 versus 135.8, 81 versus 108.4. So I do see some discrepancy between the observed counts of my data and what I would have expected those counts to have been had there been no association. So the way that we formally define the discrepancy, either the discrepancy in the segmented bar charts or the discrepancy between the contingency table and the table of expected counts, is as follows. What we do is for each entry in the contingency table, we look at the observed count, subtract off what the expected count was, square that, and divide by the expected count. And so this number here, the discrepancy, tells us kind of how different the observed data is from what we would have expected by chance. So what we look at to determine if the association is statistically significant is the p-value of the discrepancy. And this is an important thing for you to know. You want to be able to define and explain what the p-value of the discrepancy means. Well, here's the definition. The p-value of the discrepancy is the probability that a random sample would produce a value of d at least as big as what was observed from your data. Or in other words, the p-value is essentially the probability that a discrepancy at least as large as what was observed would happen just by chance. We'll talk about how you get that p-value in a second, but if you remember our golden rule for when something was statistically significant, if that p-value was less than 5%, we say the association is statistically significant, since it's unlikely, there's less than a 5% chance, that such a large discrepancy between the observed and expected counts would happen just by chance. If that p-value is 5% or greater, we say the association is not statistically significant, since it's relatively likely that could just happen by chance. We don't need to invoke an association to explain that discrepancy. Okay, so here's a key thing, and something that you're going to want to be familiar with, was how we figure out kind of what values of the discrepancy can happen just by chance, and therefore how to calculate the p-value. So know the ins and outs of the permutation test and how it works. Well, basically to figure out what values of d happen by chance, we create permuted data sets where by design x and y have no association. How do we do that? Well, we randomly pair up the x and y values together. By doing that, by the randomness in that procedure, we've guaranteed that there's no relationship between x and y. So when we make the contingency table, make the table of expected counts, and calculate the value of d, whatever value of d that we measure is, by definition, a value of d that has arisen by chance. So if we make a lot of these permuted data sets, we can build up kind of a range of values that occur by chance to know whether or not the discrepancy that we measured is out of line. So for instance, let's imagine that this is my original data set here, small data set of 6 individuals, 2 guys and 4 girls. And we have our y variable, which is whether or not they agree with something. Yes, no, yes, 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 no here. If I were to make the contingency table of expected counts, I would find the discrepancy is 0.375. Okay, well, a permuted data set, what it's going to do is it's going to randomly assign x and y values together, randomly pair them up. And the way that we do that actually is just by shuffling up the original y values. So in our first permuted data set, we've kind of randomly reordered the y values here. And we can calculate the discrepancy by making the contingency table, comparing that with the table of expected counts. And in this case, we would get a discrepancy of 6. Doing this again, randomly reordering the values of y to get a second permuted data set, our value of d would be 1.5. And if we were to do that again with this rearrangement of y's, we would also get a d of 1.5 here. So by doing this permutation test, we're able to figure out what values of d occurred just by chance. And the p-value of the original discrepancy, the one you measured from the data, is just the fraction of permuted data sets whose value of d are at least as big as the original value measured. So basically the fraction of your permuted data sets whose value of d are 0.375 or bigger. Okay, and that's how we get that p-value out. All right, so what if one of those variables is quantitative, inherently numerical? Well, what do we actually do? We don't compare the entire distribution of y between each level of x. That's much too difficult. Instead, what we do to determine if there's an association is we check to see whether or not the typical values of the distribution of y are identical between each level of x. And so we need to figure out, well, how do we best measure the typical value of a distribution? There are 3 ways to do it. Well, if all the distributions are roughly symmetric and don't have any extreme outliers, the best way to get the typical value is looking at the average. So we'll compare averages. If the distributions are roughly symmetric and at least one of them has extreme outliers, well, the best way to actually get the typical value is to look at the average rank of the values. So instead of the original values themselves, you rank them from biggest to smallest, 1, 2, 3, 4, up to n, and you look at the average rank. If the distributions are very skewed, well, you're going to want to compare medians, because the median gives a much better idea of what the typical value of the distribution is instead of the average there. So key points, know what you're supposed to compare when you're doing a test for an association between a categorical and quantitative variable. there'll be a question on that. Okay, so how are we going to figure this out? Well, we look at the side-by-side box plots. And we look to see, okay, well, is the distribution roughly symmetric? Are there extreme outliers? What should I be comparing? So in this case, what I see is on these left two plots here, most definitely these box plots look to be roughly symmetric. This median is a little bit below the center of the box, but not too bad. There's no outliers, so I would definitely be comfortable in comparing the averages between the different levels of x in this case. Over here, well, I do see a little bit more skewness, since this line, the median here, is a bit below the box. But the whiskers aren't completely different in length, so I would still actually be fairly comfortable comparing averages between these levels here. Okay. So we suspect an association to exist if there is a noticeable difference in the typical values. And actually, even though I just talked about, hey, we should be using averages here to calculate the typical value, we're actually always just going to be comparing the medians in the box plots. Do we notice a significant difference in the medians between the levels of x? On the left and on the right, yeah, looks like there is a pretty big difference in median, so I would suspect an association. Knowing what level of x I'm looking at really does inform me of what the typical value of y might be. They're different between the different levels. This one, no, the difference is fairly small here. Okay, so the larger the difference in the medians, the stronger that association is suspected to be. And we can follow this up with a statistical test. And I'm only going to focus on the test comparing the averages, because that's typically what people do. How does the test proceed? Well, just like the test for two categorical variables, we're going to compare something we observed from the data to what we would have expected to have seen had there been no association. And specifically, we calculate what's called the F-Statistic. The F-Statistic is the ratio between the observed variance in the group averages, how different they are, to the expected variance of the group averages had there been no association. So the larger the value of f is, the more evidence you have for an association, because the greater the variability in group averages compared to what you would have expected if there was no association going on. Okay, well, we know that even when all the levels of x have the exact same fundamental underlying average, they're still going to have different averages when we take a sample, just by natural sampling variation. So we need to figure out, okay, what values of f can occur just by chance, by natural sampling variation here. Well, we can run that permutation test once again. So imagine my original data. We have gender versus some number here, y. We can calculate the value of f from our original data, and then we can make a permuted data set by randomly pairing up x and y values together. So what I'm going to do is I'm going to randomly assign one of the observed values of y that I've seen before to each individual. So here's a random reordering of the y values, and if they're reordered that way, well, my value of f is 0.1. If my values are randomly reordered this way, my value of f is 6.0. So after a lot of permuted data sets, I can look to see, well, what is the distribution of the values of f that occurred just by chance? And I can calculate the p-value of my value of f from the data that I collected by looking at the fraction of permuted data sets whose values of f are at least as big as what I measured. So that p-value is the fraction of the permuted f values that are 3.1 or bigger. So what I could give you a plot of the sampling distribution of the values of f that occur just by random chance, and you can compare the value of f that you observe to the values of f that just occur by chance. Here we see that the value of f we observed is highly out of line with the values that happen just by chance, so we would see that the association must be statistically significant. The observed variability in the averages is way bigger than what you would have expected just from natural sampling variation. So you can get it graphically if you're given this plot, or you can figure out significance based on the p-value. That p-value is the probability that a value of f at least as big as what you measured from your data would happen by chance. Once again, if that p-value is less than 5%, the association is statistically significant. Now, it may not be strong, the difference might not be large. Always go back and look at those box plots to determine whether or not the association is strong or of any practical significance to you. If that p-value is 5% or bigger, well, the association is not statistically significant. It doesn't mean that there's no association, it just means that if there is one, it's too weak to be detected. So if it lacks statistical significance, obviously it has no practical significance because it would be too small to really care about. Okay, I'm not going to talk about the procedure for the rank-based test or for the median test. The only important thing you guys need to know about is which test should you be using. Should you be comparing averages, the mean ranks, or the medians? And that all depends on what the distribution of the y values are for each level of x. Okay, so what if both variables are quantitative? Well, in that case, what we're going to do to measure the strength of the association is to calculate either Pearson's correlation coefficient R, if the scatter plot looks to be well described by an ellipse, it's linear, or Spearman's rank correlation, and that works for curved relationships as long as they're still monotonic, meaning that they don't double back on themselves. So things you need to know, make sure you can look at a scatter plot and talk about the stream of points intelligently, the direction, if it's positive, negative, the form, if it's linear, nonlinear, and if it is nonlinear, monotonic versus non-monotonic, and how strong the relationship looks to be just based on the amount of scatter. We know the more scatter there is, kind of up and down, the weaker that relationship really is. I'll expect you, based on our output, to be able to find the p-value to gauge the statistical significance of the association. And as we know, statistical significance and practical significance are two different things. I want you to be able to look at the scatter plot and even calculate R squared to tell me whether or not that correlation is strong enough for you to care about. So just some slides as a review. The direction of the relationship talks about the trajectory of the stream of points. If it's going up and to the right, we say the direction is positive. If it's going down and to the right, we say it's negative. Doesn't matter if it's curved or linear, as long as it's kind of up and to the right positive, down and to the right negative. So that's why this one's positive. Some are a mix of directions. This one's positive for the first half and negative for the second half. So it's not consistent there. We talk about the form. If it's linear, in other words, the trajectory is well described by a straight line, like we have here, or if it's nonlinear, if there's some sort of curvature. If it's nonlinear, we talk about whether or not the curve is monotonic, in other words, if it's increasing everywhere, or if it's non-monotonic, where it has increasing parts and decreasing parts. And we talk about the strength of the relationship based on the amount of vertical scatter that we see. So the smaller the amount of vertical scatter, the stronger that relationship really is. And the steeper that trajectory looks to be, the stronger the relationship is as well. Okay, the other thing you want to talk about is unusual features you might see in a scatter plot, because that can complicate the analysis. These left two panels here show heteroscedasticity, where the vertical spread up and down is unequal as we scan left to right. So the scatter up and down on the left here is very small compared to the amount of scatter that we see on the right. And same thing over here. We would say that this relationship displays heteroscedasticity, unequal vertical spread. We know that correlation is not appropriate for describing that sort of relationship. We need something that's more well described by an ellipse. We'd have to use Spearman's rank correlation in either of these cases. And we also talk about whether or not there's outliers. So here's an outlier, points that are very far removed from the overall cloud here. We know that those can catastrophically affect our analysis. So here's some properties of Pearson's correlation. Things that you really need to know is when you're allowed to use it to quantify the strength of the relationship. And well, that's when the relationship is linear, where that scatter plot is well described by an ellipse. So the correlation coefficient can go between -1 and +1. The farther away from 0 that correlation is, the stronger that relationship is. So a value of 0 indicates no linear relationship. However, it doesn't mean that there's no association going on. You'll see a slide in a second where two variables have a very strong association, but the correlation is 0 because that relationship was nonlinear. So Pearson's correlation really only does a good job of describing the strength of a linear relationship. And once again, the sign of the correlation talks about if the direction of the trajectory is positive or negative. So I mentioned this before. We use the specific word correlation to describe a particular type of an association. An association in general is just used to describe when two variables are related to one another. A correlation is a specific word for when the two variables are quantitative and the average value of one changes linearly with the other. Okay, so examples of correlation. This is what different correlations look like. Be prepared to look at a scatter plot and tell me approximately what that correlation is equal to. Here are some examples where we obviously have a strong association going on between x and y, but the correlation is still measured to be 0. Why is that the case? All these relationships are nonlinear. Pearson's correlation R never going to do a good job at describing the strength of nonlinear relationships. So how do we interpret the correlation? Well, here's something you need to know. We actually don't look at the value itself. Instead, we square it. The square of the correlation is called the coefficient of determination, and it tells us something important. It tells us the percentage of the variability in individuals' y values that can be attributed to differences in their x values. Or informally, knowing x gets you r squared of the way there to knowing y for whatever reason. Remember, correlation, association analysis, there's never any implication of cause and effect. Statistics can never establish cause and effect relationship. It can only describe how strong the association happens to be. Who knows why that association exists? All right, so practical significance of a correlation. Well, the larger the value of r squared, the more practically significant it is. If you get an r squared of, say, 40%, 60%, that's pretty good for business analytics. 20%, not so great, but what value of r squared is practically important for you is still subjective. All right, here's an example where we calculate r squared and interpret it. You guys can read that on your own. Going along with the correlation is not the same thing as causation. We've talked about the existence of spurious correlations that are obviously not due to cause and effect, but just happen to occur. It's going to happen. There can always be a lurking variable. You can get a strong correlation by chance. We know that just because two variables have a strong association or correlation doesn't mean that they have a cause and effect relationship. Doesn't mean they don't, doesn't mean they do though. All right, so we've talked about that. How do we gauge the statistical significance of an association or a correlation? Well, same idea, the same permutation test here, where we generate a new permuted data set by randomly pairing together the x and y values, calculate the correlation for that random sample, and repeat that many times. So the resulting possible values of R that result, what we call the sampling distribution of R, tells you what values of R occur by chance. And so the p-value is just the fraction of those permuted data sets that happen to have at least as strong a correlation as what you actually observed. Now here's a key thing. At least as strong means at least as far from 0 here. So make sure you can define and illustrate what the p-value of a correlation is. The p-value of a correlation is just the probability of obtaining a correlation at least as strong as the measured correlation just by random chance. If that p-value is less than 5%, the correlation is statistically significant. If it is statistically significant, look at r squared to see if it has any practical importance. Okay, here's an illustration of making those permuted data sets, randomly pairing together x and y, calculating the correlation between them, and then looking to see, well, what values of r happen by chance, and then calculating the p-value. The observed correlation in this case was 0.94, so the p-value, or the fraction of those permuted data sets whose correlations were 0.94 or bigger, or minus 0.94 or smaller, at least as strong as 0.94. All right, so when we don't have a linear relationship, we can't use Pearson's correlation. If that relationship is still monotonic, we have a recourse. We can use Spearman's rank correlation. If the relationship is non-monotonic, well, you're out of luck. How does Spearman's rank correlation? Well, we take the original data values and replace them just by their relative ranks. We replace the smallest value in the data by a 1, the biggest data set, the biggest value by the sample size. We do that for x and for y, and we calculate the correlation between the ranks. The test of significance proceeds very similarly to the test for Pearson's correlation. All right, so I'll stop this section and continue on with a review of regression.